Okay, good morning. Thank you for coming. This panel session is called What's New in Aerospace, and my name is Richard Worsfold. I'm a Director of Business Development at OCE, and I welcome you to this session and hope to encourage you to ask questions and those types of things. If you have a question when it's your turn to answer the questions, you have to go to that microphone because we're recording the whole session, okay? If you are technical savvy like all the young people are, you can do #OC Discovery, and you can also do some tweeting on this, but that's all for all you young people. Okay, in this session we're going to hear from industry representatives that are going to talk about their new and exciting R&D projects that are underway with OCE, and it was part of the OCE CARIC program that we launched 18 months ago. And the idea is that with OCE is we're bringing academic researchers and industry together to identify opportunities to collaborate on, and they basically are opportunities that solve industry problems and solve industry needs, which is the whole purpose of what you're going to hear about today. I am just your host, and I'm going to introduce you to our moderator, Moira Harvey, and she is the new Executive Director of the Ontario Aerospace Council. And please go down and visit her at her booth and sign up if you're not a member of the Ontario Aerospace Council.
Absolutely.
Moira held a senior position with Messier Bugatti Doughty, and she has worked extensively with both large corporations and SMEs, and she was a business owner. So she has a well-rounded perspective on what we're going to be discussing about today. And she understands fully all the problems and the requirements and the necessities of working in the aerospace industry. Welcome, Moira, and please take the podium.
Thanks. Thank you for the introduction, Richard. Good morning, ladies and gentlemen. Thanks for joining us to find out about what's new in aerospace. So as Richard mentioned, the OAC and OCE have a long-standing collaborative relationship to further aerospace R&D in Ontario. And our panel today is comprised of 4 companies who participated in the Ontario Aerospace Technology Roadmap Workshop and Partnering Forum back in September 2013. Out of the forum, key research focus areas for Ontario aerospace interests were identified as advanced and engineered materials, advanced manufacturing, autonomous systems, electric power, ergonomics, simulation methods and tools. After the forum, OAC and OCE issued an Ontario Aerospace Challenge to industry and academia for EOIs in these focus areas. Funding was made available through industry, OCE, and NSERC. We received 29 EOIs, and they were all reviewed externally. 14 proposals were requested, and 4 projects were awarded, and all are currently underway. Our speakers today are the industrial partners for these projects, and they will share with us the status of their projects, expected outcomes, and why this method of funding supports their activities. So it's my pleasure now to introduce you to our panel members. If you would like to see their full biographies, please check the Discovery mobile app. So our first panelist is Jonathan Hack. Jonathan is with Bombardier Aerospace. He is the Strategic Technology University and Government Relations head. Okay. Jonathan joined Bombardier in 2010 after an extensive career in the automotive industry with General Motors, both in Canada and internationally. At his role at Bombardier, Jonathan is responsible for innovation and patent activities and the strategic technology portfolio for projects for Bombardier's Toronto-based activities. Our second panelist is Dr. Marianne Romanski, Operations Excellence, Technology and Innovation Senior Manager at Celestica. Marianne's current responsibilities include the development and execution of Celestica's new process technology portfolio, industry academic partnerships and networks, and the creation of customized strategies and techniques for quality and functionality improvements in new products. Our third panelist is Zhenning Liu, Senior Principal Engineer at Honeywell. Zhenning has over 20 years of aerospace engineering experience in the fields of real-time control systems, motor design and drives, power conversion and distribution, and digital designs. He is currently the aircraft power distribution portfolio leader responsible for research, development, and technology demonstration of advanced distribution technologies to TR Level 6 at Advanced Technology Honeywell Aerospace. Our fourth and final panelist is Doug Sinclair, founder of Sinclair Interplanetary. Doug has a master's degree in satellite engineering from the University of Surrey in the UK. After working in the industry for several years, he founded Sinclair Interplanetary in 2001. Working from a lab in downtown Toronto with 4 employees, Doug manufactures attitudes, determination, and control equipment for small spacecraft. Currently, his equipment is on orbit aboard 40 satellites. So welcome to all of our panelists. Thank you for joining us today. And now each of our panelists will present their topic, and I would ask that we save all questions for the end. Thank you. Jonathan?
So thank you for this opportunity to talk a little bit about Bombardier and the project that we're doing with OCE and the Ontario Aerospace Council. Now, how do I handle the slides? I just click on
the little
the green
okay. Button. There you go.
Perfect. Okay, Bombardier is the largest manufacturer of planes and trains anywhere in the world. We look far ahead to see and shape the future of mobility. Our goal is to continuously find better ways to bridge distances and people together. We do this through continued innovation in our products, and we like to say innovation is part of our DNA. When I say Bombardier, the first thing you should think about is mobility solutions. If you've traveled by plane, subway, or streetcar to get here today, you're a Bombardier passenger. Our tagline is the evolution of mobility. If we focus just on aircraft, Bombardier has launched 32 new aircraft programs since our entry into aerospace in 1986. We compete in both the commercial and business aircraft sectors. We have approximately 7,000 business and commercial aircraft flying all around the globe today. Our business jet portfolio is the most comprehensive in the industry. We have sold almost 4,500 business jets globally. Our largest business jet, the Global family, is built right here in Toronto to what we call the green aircraft stage. We then fly them to Montreal and we paint them, and the interiors are upfitted for the most demanding and high-end customer applications anywhere in the world. Every 3 seconds, a Bombardier aircraft takes off or lands around the globe. Our current fleet is, again, more than 7,000 aircraft. So that completes the company introduction and advertisement for Bombardier. But what I'm here to talk about today is our project called a flexible, reconfigurable cabin. When the government of Ontario announced the Aerospace R&D Challenge, we thought that Bombardier, as the largest OEM in Ontario, should participate. With the recent increased focus on cabin comfort as a differentiator in aircraft sales, we developed a proposal with Ryerson University, Queen's University, and the University of Toronto that focuses on cabin comfort from a passenger perspective. And we titled this the Flexible Reconfigurable Cabin. I'm sure that many of you have been on the internet and you've seen the recent design renderings done by various companies on future aircraft and future aircraft cabins. These futuristic designs are airy, bright, and offer high technology interfaces which surround the passenger. Everything is at the passenger's fingertips with unlimited connectivity and information interfaces, no matter where the customer is flying from or to. The future cabin is as modern as the technology that provides lift and stability to the overall aircraft structure. Unfortunately, however, the experience of many people who fly today is somewhat disconnected from that experience. The aircraft cabin today has evolved to become an increasingly crowded space with a focus on carrier operating costs, which can frequently result in a less than optimal experience for the customer. Comfort is an individual experience. There are many components to personal comfort. Before starting this project, and in order to not have it just focused on engineering technologies, we engaged with Ryerson University, their Faculty of Architecture, to do a preliminary project to look at comfort of people in enclosed places. And we learned an awful lot through that engagement. We had an intern that was employed full-time at Bombardier for a period of about 6 months that helped us with that project. And what we learned is that comfort is very important because people's perceptions of comfort depends on the amount to which they can control their immediate environment. This project will then focus on, we obviously can't do all areas of cabin comfort, so we're going to focus on the optimization of aircraft seats, individualized cabin management and control, and also an entertainment zone for business aircraft. So as far as the seats go, we understand that seat comfort is an individual experience. What is comfortable for one person is not comfortable for another. Accordingly, in addition to studying how to make the seat more mass efficient, we are looking at new feature addition and responsive design centered around personal seat comfort, utilizing the morphing technology that's been developed at Ryerson University. The aircraft seat is one of the most important elements of comfort during a flight. It's a crucial interaction point for the customer with the aircraft. The focus here is on how to optimize some of the technologies that Ryerson has developed in terms of mass efficiency, features, and comfort in the aircraft. We also understood through our initial project with Ryerson that perceptions of comfort can be modified by using effective use of lighting and window technologies. These factors are important in providing an overall cabin ambiance while providing individual control according to what the customer wants to do while he or she is flying. There has been much work done by supplier companies on various technologies to replace cabin window shades, those clunky plastic things that you've got to haul up and down manually. And so there are some integrated technologies now that will dim and change the color of those windows automatically and instantly. We're also looking at LED lighting and distributed lighting concepts to augment the passenger space in the cabin. Last of all, we're looking at a cabin entertainment zone. And I've got some renderings there. This is actually the inside of our global business jet. Business jets are flown by the most demanding aircraft travelers anywhere in the world. And so they're looking to have a personalized space where they can do absolutely everything on an aircraft that they could do in their homes. Projection and display technologies have evolved substantially over the past decade. Passengers are demanding a premium sound and theater experience in the air. We're looking at OLED technologies, projection and display technologies, and how can we integrate those in a cabin in a way that's going to provide that same kind of premium experience that customers demand. The key to this project is going to be the integration of all of the above concepts. Technologies are going to be analyzed in a laboratory environment and then validated through a full-scale mock-up. We're donating a full-scale C-Series cabin mock-up for a commercial aircraft to Ryerson University for work on this project. And so we're going to take the technologies that are developed in the lab and we're actually going to physically demonstrate them in a passenger space. In terms of next steps, Bombardier is working with OCE in Ontario and other nationally based programs to further technology development in the cabin, working together with Canadian SMEs to develop next generation's technologies for key strategic areas in the cabin. This unique type of partnership between an SME and an OEM integrator outside of program development initiatives is really critical. We're working with local governments to establish an innovation zone for targeted technologies at Downsview Park as well. Our new C-Series commercial jet has demonstrated many new technologies for the aircraft cabin, and subsequent programs such as the Global 7000, which are made right here in Toronto, will continue to build upon this momentum. Our plan at Bombardier is to ensure that this expertise continues to grow here in Ontario. And we think through continued investments in programs like this, we can ensure that that is able to happen. With programs such as the OCE Aerospace Challenge, we are well positioned to continue with this type of activity right here in Ontario. Thank you for your time today.
Thank you, Jonathan. If I can invite Marianne up now.
Okay, and it's the green button, right?
Green button is forward,
Great.
yeah.
Okay, thanks. Thank you for the invitation to speak today, and we're going to be talking about environmentally compliant electronics next in terms of what's new in aerospace. And this is another one of the projects that was funded through the joint OAC and OCE funding collaboration. So a couple of words about Celestica in the beginning. Celestica is a 27,000 person strong company. We're one of the 10 largest electronics manufacturers in the world. We manufacture for folks like IBM, Cisco in the enterprise space. We have done products for BlackBerry and Microsoft in the past in the consumer space. We build solar panels and inverters, a wide variety of industrial products for folks like LG. And we also, of course, build for the aerospace sector. And we're one of the top manufacturers for the aerospace sector globally in terms of the electronics that we produce. So we have a very strong history, about 15 years out of our 20-year existence as a company in building in this sector. Now, there's a lot of regulatory compliance that goes along with being a manufacturer for the original equipment designers, and one of our main objectives is to ensure the reliability of the products that we build. That's really one of our prime criterion. Cost, of course, is always an important factor, but product reliability and compliance to regulations is very important for the products we build in this sector. So if we take a look at the types of products that I mean, we, as Celestica, as an electronics manufacturer, we build things like entertainment systems. So Bombardier designs, some of those systems, but we will build the electronic guts of them. We also build things like landing lighting. We'll also build cockpit controls and a wide variety of other systems that you can see kind of in the tip to tail diagram here. So there's really dozens and dozens of systems that are run on electronic controls that Celestica produces. Now we have several centers of excellence across the world that specialize in aerospace electronics. So one of those centers is right here in Toronto. And we also have other centers in Spain and in Malaysia. So the technology that's developed for the manufacturing hardware technologies right here in Toronto is then promulgated to our other locations across the world. So what's the challenge that the electronics hardware part of the industry is currently facing, and what's the point of this project? Well, there's a lot of environmental regulations right now that have affected aerospace electronics, and not necessarily directly. It's because electronics really has a large supply chain that is heavily influenced by consumer goods, as well as industrial and enterprise products. And when those products encounter regulations about the types of materials that are allowable, it eventually impacts this whole supply chain for the electronics hardware. And really, electronics hardware is governed by essentially material physics when it comes down to it. So when an environmental regulation is made, it eventually ends up affecting material reliability through the actual atomic level properties of the materials that are used. So the RoHS regulations down in the left-hand corner really spawned a whole new area of research for the electronics industry as a whole. And then the US government, Department of Defense, back in the mid-2000s, thought it was important enough to focus a group of 15 world-renowned scientists to create the book that's shown there, the Manhattan Project, and there's other industry groups such as PERM, which work to develop some of the new hard electronics materials that are required. So the problem what this project is looking at is that electronic materials don't always age well. So people age, we understand some of those mechanisms. Well, electronic materials also age, and we're trying to understand some of those mechanisms in terms of what effect does it have on hardware reliability. So a little bit of a schematic about what we're trying to achieve in the research and technology development that is being funded by this program. We're looking at really the atomic level changes that are found as solder materials age. So solders are the interconnects upon which all electronic devices are based. And if those age and if they break under stress, then we run into reliability problems, we run into physical breakage, essentially. So we're looking really at the microscopic level to see what impacts breakages that can occur and cause obvious product failures. So along the bottom you'll see examples of some of the types of microscopic images that our partner in this work, the University of Toronto, is doing for us in terms of understanding what the materials are. So in terms of what aspects Celestica is contributing to the project, we're looking at how to assemble products in the most reliable fashion and what type of environmental testing we really need to do. Do we need to do vibration, mechanical, tensile stress, really simulating an aircraft environment under a wide variety of conditions to make sure that whatever new materials it is that we're proposing are actually going to be as safe as we all expect them to be. Following on to that work done at U of T, the next step then really is take those findings and put them into industry standards for building those products. So IPC is just one example of the types of standards industries that we're heavily involved in and to whom we deliver a lot of the reliability results that are going to come out of this work. And again, jointly with the University of Toronto, who's been working in this area for many years. So just in summary, the type of work that's described here is really a result of many years of sequential efforts by a large number of companies, and the current funding really builds on that work and the good work done at University of Toronto. And at the end of this, we really are expecting to have an outcome that can go and be disseminated into the industry groups in terms of recommending which material it actually is that we can recommend. So thank you very much for the opportunity for the funding, and we'll be publishing the results in about 2 years. Thank you.
Thank you, Marianne. Zenning, if I can invite you up next.
Okay, thank you for coming. The project I'm going to talk about is the high power density converter for aircraft application. And this is in collaboration with University of Ryerson University, and of course with the help with OCE funding. Here's a little background for the project. We know more electrical aircraft has become the trend for modern aircraft design. And the idea to use electrical equivalents to replace the hydraulic and pneumatic equipment provide the opportunity for further lowering the maintenance cost, reducing the fuel consumption, and improve the reliability and improve the aircraft functions. The more aircraft technology content, more electrical aircraft technical content, usually is classified into 6 categories. But here what's important is power converters were involved in almost every category. So power converter is one of the most critical technology elements in the more electrical aircraft concept. One of the major challenges facing the more electrical aircraft concept is the converter overweight, which compromising the more electrical aircraft benefits. Because the electrical equipment generates heat and we need the cooling to take those heat out. So that adds the weight to the equipment and as a result offset the benefit. So this drives the demand for high power density power converters as well as high efficiency power converters for aircraft application. And this also forms our project focus. Give you an idea, I cannot go back. So the existing state-of-the-art technology is, the power density is about 9 kilowatt per kilogram, and our target will be 15. So we're still far from there. So our project is directly targeting a new aircraft equipment, which is called the electrical taxiing system. And the idea is basically putting the electrical motor into the wheels of an aircraft and using motor controller powered by the APU power so that the aircraft can basically drive itself by itself from terminal to the runways, and from there, and the main engine can start. So during the whole period of time, main engine is off. So that's how we try to save the fuel. But the problem with this is this motors and the motor controller are add-on equipment. So the weight of those equipment is very critical to the success of the program. So this is our project scope. So this a typical power converter is like this. So it contains the input-output filters and AC to DC converters and DC link and the DC to AC converters. Usually, this is the typical conversion. So our original collaboration with university can only focus on component level improvement, such as how to reduce the filter size and how to reduce the heat sink for the power switching modules. But with OCE funding, it allows us to expand our technical scope to look after every aspect of the converter system and to be able to achieve the system level optimization. This is our technology now. Right now, the technical scope is covering all 4 areas. And for example, we're going to study the converter topologies and to decide which one is best suited for our application. So we may select the topology which has heavier power switching modules, but end up maybe saving the filters completely. So overall, we can still achieve the weight savings. So the project has been kicked off for more than 6 months. So we have completed requirement capture for the targeting platform, and we have completed the studies for all 6 different topologies and eventually selected the one that we liked. And we actually designed and built a prototype and functional test them. So right now, this prototype just has been delivered to Honeywell. It's in the Honeywell lab, and we're going to do all kinds of evaluations, including full power test. So finally, in conclusion, one of the major challenges facing more electrical aircraft is the onboard power converter overweight, which compromising the benefit that we can. So this is our project with Ryerson is intent to address this very issue and targeting a very new electrical equipment or systems, and to achieve anticipated reduction in fuel burns and emissions. And finally, with the OCE help, it allows us to extend our research scope and be able to look at the system level and to achieve the best result, which is the high density of the converter. Thank you.
Thank you, Zenning. Doug?
Thanks.
Thanks.
Hi there. I'm going to talk to you today about a new attitude control system for the next generation greenhouse gas monitoring satellite demonstrator. So I'm going to talk about Sinclair Interplanetary, who we are, what we do, and then the opportunity, solution, enabler, and benefit of the project, where we are actually today, and then some concluding remarks. So Sinclair Interplanetary, I'm Doug Sinclair, this is my company. Founded in 2001, started off very small and have grown a little over the years. So what we do is we supply hardware, software, training, and some consulting to the spacecraft community. So what we don't do is build complete satellites. We build little bits of satellites and give them to other people that make full satellites. But the satellites that we concentrate on are nanosatellite and microsatellite missions. So physically, what does that mean? A nanosatellite might be this big. A microsatellite might be this big. So these are spacecraft that you can pick up. And this makes them, this allows them to be built in really quite a different way from the sort of school bus-sized satellites that the flagship programs are running. So the budgets are constrained, the development timelines may be very short, and we can typically use higher and newer technologies than you could in a big traditional spacecraft. So the sort of products we make, reaction wheels, sun sensors, magnetorquers, stir trackers. So we've got 38 satellites under the Sinclair Interplanetary brand, which isn't quite the same number as in my bio, which is my personal satellite count. And we sell to Canada and everywhere else in the world, really. So let's talk about the opportunity here, what we're trying to do. It wasn't that long ago when microsatellites and nanosatellites had no pointing capability at all. So you just pop them up into space and they would tumble around. And if all you had on that satellite was a radio, maybe you didn't care that it was tumbling. But now we're starting to think about putting things like cameras on the satellites. If you've got a camera on a satellite, well, you've got to point that camera at the target that you're interested in. So over the past decade or so, bringing pointing capacity to small spacecraft is now relatively routine. So we've got space telescopes that will point at a particular star, and we've got lots of satellites with cameras that will point straight ahead, or cameras that will point straight down. What we're looking at doing here is target tracking, where the spacecraft has an instrument that can look at a target on the ground, and as the spacecraft flies over that target, it will track it down and then behind. So spacecraft is bombing along at probably 7 kilometers a second at an altitude of maybe 600 kilometers, and you want to keep your instrument targeted on a particular point on the ground. So that's what we're trying to do, and that opens up lots of capabilities for small satellites if you can do this. And so the one example we're looking at here is greenhouse gas monitoring. If you can point a payload at a particular industrial site on the ground, so a cement factory, a tailing pond, something like that, and if you can make a direct measurement of the amount of greenhouse gas being emitted by that site, that is a commercially useful thing to do. So the way that we do this, we basically reach into the toolbox of existing components. We'll start with the thing pictured on the bottom, a star tracker. Star tracker, it's essentially a little camera. You put it on the side of your satellite, looks out at space, and it sees the stars. And by looking at the pattern of the stars, it can recognize what stars they are. And I can say, this is the Big Dipper, there's the Polestar there. And you can, this little box will very accurately tell you what direction you're pointed in. So that's one half of the problem. I know now where I'm pointed, but now I want to change my pointing and point at the direction that I'm trying to point my instrument. So for that, we use something called a reaction wheel. So those are pictured at the top of the figure. Reaction wheel, essentially an electric motor and a big massive flywheel. If you accelerate that wheel, you speed it up, you put torque on it, you're putting an equal and opposite torque on the body of your satellite. So if I've got 3 wheels mounted orthogonally and I change the speed of each of those wheels, I can point the body of my satellite, and thus my instrument, anywhere that I want. And we're not using gas jets, we're not using rockets. So we don't have a tank of gas that we're consuming. Instead, we're just using electrical energy to power these things, which are coming from the solar arrays on the satellite. It's essentially a renewable resource. The spacecraft now does not have a constrained lifetime. The spacecraft is going to last either until it burns up in the atmosphere or until some electronics failure takes it out of commission. So what we're doing is we're taking these existing building blocks and we're putting them together to make a system that lets this small satellite track a ground target. So we're doing this in collaboration with the University of Toronto Spaceflight Lab. So they are building the bus for the GHGSat satellite. And then GHGSat Incorporated is the company that is putting together this demonstrator of a commercial service. And then we're working together with, of course, OAC and OCE and NSERC, who have very kindly contributed some funds to make this all work. So GHGSat-D, which is the demonstrator, will be a single spacecraft that can make these measurements of greenhouse gas production at source. And so that's a demonstrator for a planned constellation of a number of spacecraft that will allow for monitoring of various industrial sites and will support a commercial service. So the benefits of having this capability, of having the ability to point a spacecraft at a particular target on the ground, what it does is it lets you do a mission that traditionally would require a large spacecraft, which is usually doing something like a push broom imager, collecting a huge swath of data. Instead of having to fly a big spacecraft, you could fly a much smaller spacecraft and target the particular things that you want to look at. So it's increased availability for services, and then for everybody else involved, for the bus manufacturers of the University of Toronto, for component manufacturers like me, everybody wins from this. So the project status. GHGSat-D, this first spacecraft, we're about halfway through the project right now, and GHGSat-D is almost ready to go. So the attitude control system's been put together and verified in simulation. We've got the hardware together. The spacecraft you can see there, sitting on the bench, it's built, and we're looking for a launch late this year. So in early 2016, we'll actually have this up on orbit, and we'll get the data back, and we'll see whether it points in the right direction. We'll actually be able to validate the project. So in conclusion, GHGSat and the University of Toronto and Sinclair Interplanetary, we've come together, we've put together this state-of-the-art pointing package for nanosatellites and microsatellites, and we're going to demonstrate it on GHGSat, but of course it then remains available for use on all sorts of other satellite missions. Thank you.
Thank you, Doug. So I think we have some time for some questions now. One of the things that maybe we could start the question session off with is, we've talked, I think all of you spoke in your projects about environmental impact. And I wonder if you could maybe just take a moment and let us know what type of environmental impact is your project delivering. So I think everyone is working to become more environmentally responsible, and how does this project kind of tie into that? Jonathan, will we start with you?
One of the focuses at Bombardier is on increased environmental performance of aircraft. And so probably a key aspect of this project is seats can be very heavy, and they tend to be over-designed. And when you multiply it by the number of seats you have on an aircraft, the outcome of that is you have to consume more fuel to move that inertia a given distance. And so what we're looking to do is a very intensive topology optimization and materials study on seats so that we optimize the seat and get it as lightweight as possible while still meeting the certification requirements.
Thanks. Marianne?
Yeah, at Celestica, in addition to environmental sustainability programs that we have in our various manufacturing factories, we also need to comply with regulations that are global that affect electronics industry. And one of the primary ones that's affecting this particular project that I discussed is taking lead out of electronics. And electronic solders are primarily were based in lead and tin, and we're now taking that lead out of the systems, so that it doesn't eventually end up in, as a waste product in landfills, et cetera. So we're taking the lead out and replacing it with tin, and that's one of the big challenges that we're looking at is how do we make sure that our electronic systems still work and maintain the environmental compliance aspects too.
Thanks. Zenning?
Yes, as I mentioned, our targeting platform is an electrical green taxi system, which has a very significant environmental impact, in fact. It's estimated for one aircraft in the category like Boeing 737 or A320, in 1 year it can save 200 tons of fuels. So if you count the similar type of fleet all around the world, it's estimated at least we can save 3 million tons of fuel in 1 year.
Wow.
Yeah.
That's impressive.
Yeah.
Big number.
Yeah.
Doug?
So what we can do with these small satellites is we can look at the Earth and we can just get a better understanding of what's going on the planet. So with the particular example of GHGSat, which is a spacecraft that's under construction at the University of Toronto right now, what that does is measures greenhouse gas production at source. So you look at a particular industrial facility and you can find out how much CO2 is it making, how much methane is it making. And so that's not reducing emission by itself, of course, it's just measuring it. But that's the first step. You have to know what you're doing in order to understand what facilities would benefit from modification to reduce their greenhouse gas emissions.
Thank you. And anyone in the audience have a question? We're going to ask you to go to the mic with your question. So a line up there anytime now would be good. Go ahead, sir.
Hi, I have a question for Marianne. So ROS directive has been around for quite a while, at least 12 years. So and reliability impact of switching to tin-based solders is reasonably well understood for typical applications like, home electronics, etc. So I understand that your project was looking specifically at the issues around aerospace type of applications that are not typically seen in normal, regular electronics.
Yeah, so the first issue with aerospace electronics is, number one, the expected lifetime. So, I think most of you have experience with electronic products, particularly the consumer ones. I mean, their expected lifespan is about 2 to 3 years. Electronically controlled industrial devices, maybe 5 to 10 years. Let's say automotive electronics, kind of the same. Aerospace is expected to last 15 to 20 years in a lot of cases, and if not, then there's a significant repair expense that's also required, so repair and inspection. So we're looking at those much longer lifetimes that are required and what specific materials are needed for that. We're also looking at vibration requirements that are obviously quite a bit different from office environments and from a lot of the industrial environments too. So we're looking at the materials that will last specifically in those types of long life and mechanical stress situations that aren't encountered by other types of products.
Thank you. So I understand that with regards to that switch to SAG-based solders, aerospace industry is still in transition.
Oh, absolutely.
If I understand correctly.
Yeah, absolutely.
Because that transition already occurred for consumer electronics many years ago.
That's absolutely correct. Okay. And medical electronics, for example, have just been transitioning over in the last year or so. Some of the telecom products were also exempt. So there's a whole cascade or timeline of when certain industries must transition over. But as I alluded to earlier, it's not just when you must transition, it's also when the supply base is actually supplying componentry at a reasonable price point as the volumes drop for the lead-based solders.
Thank you.
If I could actually just add to that, in the space business, we haven't transitioned, we don't want to transition, we're terrified of this. Mostly due to tin whiskering concerns. And any tin surface grows these little hairs. They grow very slowly, but if you've got a spacecraft on orbit undisturbed for decades, these hairs just grow out of surfaces and form short circuits. So our supply chain has gone almost all lead-free, and we take all of our components and we dip them in lead. And we reball all of our BGAs with lead. Yeah, we're big on lead.
Yeah. Absolutely. Thank you.
Actually, Doug, I had a comment for yours. Another environmental impact that your system would be doing is that it's self-sufficient and is not reliant on fuel. So that in itself would be a big impact on the environment, I think, as well.
Sure, in that it allows a spacecraft to last a long time, so you don't have to replace it. Yes.
Exactly. And actually, I have a question for you, Sir Zenin, and it's actually about redundancy. I've had the opportunity to look at some developments specifically in landing gear, and I know that's a different application, but as they try to transition from hydraulic to electronic, but the redundancy systems that they have to put on, put on there means they're actually put almost 2 additional systems on there, so on the actual gear mechanisms. So this is not being very helpful, and so this is why that's taking a lot longer. So my question for you, sir, was what levels of redundancy are you building into your system?
Yeah, for our particular application for electrical taxing systems, we don't have a redundancy, but we do have all kinds of protection mechanism to ensure it's fail-safe and fault tolerant. But in the case of e-taxi system, if it failed, it stops there. So we told them, or we can start the engine to prepare it. So as a redundancy measure, yeah. But if we're replacing the actuators, we may have to consider redundancy in our converter design.
Exactly, and so it's the heat buildup of the additional redundancy as well, which is...
Yes. But generally, electrical system is more reliable than mechanical systems. Yeah, as long as you can keep it cool. So this is the key.
And does that require certification?
Yes.
As an add-on?
Yes. Yeah.
Thank you.
You're welcome.
Hi, Nick Danilo from Singularity Weblog. My question pertains a little bit more about the future and some of the, hopefully, goalposts that you might be able to see across industry. And for that, I just want to go a little bit in the past. One of the criticism coming from people such as Peter Thiel, for example, is that the aerospace industry has made no progress, according to him, but rather regress. The reason being that the 2 poster children for success used to be the Apollo program, a capability which we now have lost to reach the moon, and the Concorde plane, which now we also have lost. So my question is, do you see any goalposts into the future which can kind of propel the industry across the board to reach such perhaps more visionary targets? Thank you.
So I don't think we're regressing at all. We have robots driving on Mars for the past dozen years. That's We did not have that in the 60s or 70s. It's what we've lost is the ability to sling monkeys in cans very fast. Because who wants to move monkeys from place to place?
Yeah, his response to that would be, we had Voyager even before that, right? So which
Pluto
is
fast flyby.
sure, but it's out of the solar system now. So the point is that the real big jumps were done 70s and 80s and even 60s with the Apollo program, or maybe 60s with the Concorde plane. And now, I mean, I'm not saying that's the case. I'm saying that very notable figures are saying that that's one of the industry which, in contrast to the rest of the world where we have exponential growth, supposedly, the aerospace industry has been lagging behind. You don't observe that exponential growth.
I'll let somebody else be angry.
I think I would challenge the exponential growth. I mean, we're seeing just tremendous growth in terms of air travel. I think you have to factor in the tremendous regulatory regimen of aerospace when you look at development and new technology. And obviously, it's incumbent upon any manufacturer to ensure that a technology is properly validated, and that takes time. So I think there's a lot going on under the surface. There's a lot of research going on. There's a lot of work going on to nanomaterials, new technologies, but they have to be properly validated, and that's going to take time. We're also looking at new configurations of aircraft, blended wing bodies, those types of things, but then those have to be mated to a technology in airports that are able to receive them. So there's a lot of great ideas out there, but it's going to take time for the entire infrastructure to be able to respond and for you to be able to see those in everyday life.
And I think the other thing we have to remember is, as the flying public, we want the lowest possible cost in the most luxurious and comfortable aircraft we can possibly find. So we don't always encourage those developments if they're going to compromise our personal comfort, which was one of the things that Jonathan was talking about. We have time for maybe one more question from the floor.
Hello, my name is Raj Talwar. I work for the Boeing company. Very nice to hear from Jonathan about BWB. So I know all about that thing, blended wing body. Most of you folks are electronics folks, and now that we have talked about solder, lead-free solder, that was one of my questions. My second question is, what I want to ask is, several years ago, we were hearing a lot about counterfeit electronics. You know, we were all scared that the counterfeit electronics will get into our expensive systems and satellites and defense systems. And we were looking for technologies to figure it out whether a chip is a counterfeit or not. What has been going on in that area? Any new developments, any new technologies? So Honeywell and you guys can figure it out, oh, this is a bad chip or it's not made by our supplier? Thank you.
I'm not aware of any actions that we can take other than the purchase department. They need to be careful with the source of the electronics components.
Yeah.
But I don't think any component manufacturer will make any imprinted signatures in it to distinguish that. I'm not aware of that.
Yeah, so at Celestica and several other companies, we did look at technologies to identify if something was counterfeit or not. What we've realized is that there are some very interesting technologies out there that we can use for marking components. But as Zenning alluded to, it's really the supply chain that's the first line of defense. And the way that in the high reliability industries we get around the counterfeit issues, we make sure that we're buying only from sources that we've audited, that we trust, that we know are compliant, and that have full traceability. So using the right kind of purchasing logistics approach in our supply chain means that we can avoid counterfeit issues. And then, of course, there's the in-house inspection. Once it actually gets through that whole supply chain, the inspection protocols and the audit protocols that we have in-house. And then, of course, there's the product level testing where any inadequate performance is also highlighted. So there's a lot of checks and balances all the way through the whole system. We haven't yet found a need to go to some of the kind of more exotic tagging systems that are currently out there.
Okay, thank you very much. Thank you to all of our panelists, and I'd invite Richard to come back up and close our session today.
I'm here to say thank you, but I'm going to make a comment. How would you like to get on an airplane in Toronto, get off the airplane in Paris, and find out you had no pilot on board? There's a goalpost for you.
It's been about 4 years since I rode in the Google self-driving robocar, and I'm looking forward to get into the plane, but I don't see it on the horizon yet, so if you could fill us in, I'd love to.
Well, I can't fill you on a timetable, but I've predicted within 30 years it'll probably happen.
Yeah, but the autopilot technology is already existed. The airplane can drive, can take off, landing all by itself,
And
automatically.
I forgot to add that the actual guy piloting the airplane will probably be in St. John's, Newfoundland, in a nice soft spot. Well, thank you very much, audience. Your questions were great. But I'd also like to thank the panel.